Hi, everybody, and welcome to the second half of Lecture 3 on atmospheric circulation. So, what happens to the radiation once it reaches the Earth? Oops, pardon me. The equator, remember, gets more direct solar radiation. It hits it more head on, and it also gets an intense year-round supply because it's not affected by the tilt of Earth's axis. The amount of sunlight reaching the equator is the same year-round. So there is essentially a surplus of radiation and thus a surplus of heat at the equator. In contrast, there is a deficit of solar radiation and thus a deficit of heat at the poles. This creates a gradient where heat will flow from overall from where there is more of it to where there is less of it. And this happens via convection. And convection is when heat is transferred by way of being carried by a fluid as it moves, whether that be like air in the case of the hot rising air carrying heat and then transferring it to this cold window, and then the cool air falling and the air being warmed again by this. That also happens with water in the ocean, as well as with magma in the interior of the Earth. And heat can be transferred in three separate ways. Convection is one of them. We've talked about radiation, and radiation is the only way in which energy can be transferred without matter being involved. So electromagnetic radiation, like visible light and ultraviolet light, doesn't need a medium in which to be transmitted, and it can be transmitted through the vacuum of space through radiation. You can also transfer heat by conduction, which is physically touching something. And for example, if you touch a glacier, your hand gets cold because heat is transferring from your hand to the glacier. Or if you touch a burning stove, you feel hot because a ridiculous amount of energy is being transferred from the burning stove to your hand. And in the atmosphere, heat brought in by radiation actually begins to circulate via the third method, convection, once it arrives. A fluid, like air or water or magma, cycles and brings the heat with it. And so what's happening in the atmosphere is that warm air rises, it cools down as it gets farther away from the infrared radiation of Earth, and then cools as it falls. In the interior of the Earth, mantle material is warmed by the hot outer core near the bottom of the mantle, and then it rises, and then it gets cooled by contact with the crust, and it falls down. Cool mantle material falls, warm mantle material rises. And a simple initial model for atmospheric circulation involved a simplified version of this in which at the equator, warm air rises and then travels through the upper atmosphere towards the poles. And once it gets too cold to travel, it falls at the poles, and then you get surface movement of air from the poles towards the equator, where it then gets heated up enough to rise. And this is the Hadley model, the simple Hadley model. And air gets cold while it's up in the atmosphere because it's farther away from Earth's infrared radiation. The infrared radiation coming from Earth does a much more effective job of heating air than solar radiation does. And that's because the air is densest at the Earth's surface. It actually turns out that the air gets too cold once it gets up into the upper atmosphere. It gets too cold to make it all the way to the pole without falling back to Earth's surface. As it turns out, Earth's circulation system actually operates more as a series of conveyor belts than a single one. And this is the model that we have today that more accurately represents how air moves throughout from Earth's surface to the upper atmosphere and how that works at different latitudes. So we essentially have three circulation cells in each hemisphere. The Hadley cell, where hot, wet air rises at the equator and loses its moisture at the equator, and then the air continues in the upper atmosphere until it falls at 30 degrees. And there is a mid-latitude or Farrell cell where wet air rises at 60 degrees and also falls at 30 degrees. And lastly, you have the polar cells where some of the same wet air at 60 degrees instead travels to the poles and falls at the poles as cold, dry air. This does overall have the effect of transferring energy to the poles from the equator because energy can be transmitted by the air molecules in one cell, bumping up against air molecules in the next cell, but it's much less direct than the simple Hadley model, and this contributes actually to why the poles are so cold, because some energy makes it all the way, but a lot of it gets lost in the various circulation processes. And air, ultimately, and energy have a much more complicated path to getting to the pole than you would think. And notice how there's both an upper atmosphere and a lower atmosphere component. And winds on Earth's surface, as it turns out, are largely the result of air traveling from latitude to latitude. You'll also notice that they're curved, and that is a consequence of the Coriolis effect. And this is an example of how you want to consider that the air is moving at the surface also, and not just up in the atmosphere. Part of the circulation involves air traveling overall along the surface of the Earth from one latitude to the next. Now, the lines here actually showing the surface movement are curved, and that is a result of the Coriolis effect and Earth's spinning. And Earth's spinning causes projectiles, including masses of air, to not travel in a straight path, but rather to be deflected slightly, because different latitudes spin at different rates because Earth is more or less a sphere. We'll talk more about that on an upcoming slide and also in next class. And note that when warm air rises and expands and cools, it can no longer hold its water vapor, and it forms clouds and precipitation. And this is why we have so much precipitation, so much rainfall at the equator. The polar front, meanwhile, is about at 60 degrees, where you actually get a lot of wet regions like the Pacific Northwest, and the polar front. And remember that I mentioned the Antarctic convergence as a front where two masses of water meet. We also have fronts in an atmospheric context where different masses of air meet. And at the polar front, you have a lot of precipitation and cloudy, unstable conditions occurring. 60 degrees are a wet latitude where you get a lot of rainfall, same as the equator, but not quite as intense, whereas 30 degrees and the poles, 90 degrees, are where you get less rainfall. Now, the Coriolis effect causes the path of air to be curved because without it, air would more or less travel in a straight line north or south. But the Coriolis effect provides an additional force that tugs on a mass of air, either to the right relative to its original direction in the northern hemisphere, or to the left relative to its original direction in the southern hemisphere. And this force is perpendicular to the original direction, which would be either due north or due south. And this causes projectiles to travel in a somewhat diagonal direction that we end up perceiving as a curve. And this causes effects such as the eye of the hurricane. It causes the air rotating towards the low pressure center to be always deflected slightly away from the center. And it also causes deflection of air masses as well as water masses, and we'll talk about the effect on water masses in Wednesday's lecture. Now, what this is that different latitudes of Earth spin at different rates. If you have, for example, a cannonball, or you can think of it as a pilot flying their plane, because that gives you a sense to, if you're flying a plane, that gives you a way to imagine first person the direction that you're moving in. So a cannonball or a plane or a mass of air that leaves the ground will have the spinning velocity of where it was launched from. Where it was launched from, whatever latitude they're at, the Earth underneath them is spinning at a certain rate. And the Earth spins faster at the equator than it does at the poles, it turns out. When the object leaves the ground, it will retain the original spinning velocity. And if you're going from the equator towards the North Pole, the cannonball or mass of air, or the plane, if you don't correct for it, is going to continue spinning at the same speed than it was at the equator, even though as it goes north, the ground underneath it is actually spinning more slowly. And so you get deflected to the right. You are essentially spinning too much for the latitudes you're under, and you end up deflected to the right of your intended path. And remember, the Earth spins fastest at the equator, more so than at the poles, because it has to spin faster for the point on the equator to be back at the same position at the same time of day in the course of 24 hours than does a point close to the poles, because Earth bulges out at the equator. So in the example on the right, we have an instance in the southern hemisphere. In the southern hemisphere, we get a deflection to the left of the original path. Notice that the cannonball is facing the opposite direction this time. If you were in a plane, you would be going from the equator south to the South Pole. And what's happening is that this time you're still being dragged from the west to the east, because Earth always spins in that same direction, left to right, west to east. And if you're in the southern hemisphere, you're going from the point on Earth where Earth is spinning fastest, the equator, towards where it's spinning much more slowly, aka the South Pole. And your expected path is due south, but you actually get deflected a bit to the east or to the left of your original path. And the projectile is being kind of dragged by the equator in the direction that the Earth is spinning. And the fact that you get different directions in the northern and southern hemisphere relates to the fact that Earth is spinning in the same compass direction. It's spinning west to east no matter what. So you end up with a different relative direction of deflection, either to the right of you in the northern hemisphere or the left of you in the southern hemisphere, because Earth is being spun in that direction. And remember, left and right are relative terms. You have to think from the perspective and vantage point of the projectile that's being launched. Now, aside from the Coriolis effect, another important aspect that I need to introduce is relative humidity. And water vapor is dissolved in a solution in a way, because it's just one of many gases in the atmosphere. The atmosphere can hold a different amount of water vapor before it condenses and falls out as rain, depending on how hot the temperature is. Warm air actually has a higher capacity to hold water than cold air. And the relative humidity is the amount of water vapor in air relative to the maximum capacity of air at a given temperature. And the dew point is the point at which water falls out when the air is saturated. So relative humidity is going to rise as the air cools, and once 100% relative humidity is reached, the water will fall out. It'll condense as rain or snow. And this is important because rising air cools as it rises, and thus any moisture it has will largely be lost when it rises to its maximum amount, before it starts changing latitudes. Now, something else I want to mention is that rising air causes low atmospheric pressure, because oxygen molecules aren't nothing. Low pressure is caused by the oxygen molecules traveling away from the surface. And so at the equator, as well as 60 degrees north and south, the dominant force is rising air. So we have a low pressure zone. The air is relatively hot, especially at the equator, so it's rising, and thus the air is being taken away and exerting less of a force on the ground. Meanwhile, high pressure zones are by and large where relatively cool as well as relatively dry air falls from the atmosphere to the ground. The pressure is from falling oxygen molecules, and the air is that which cooled as it rose in the atmosphere and eventually cooled so much as it started to travel across different latitudes that it fell back to Earth. So at the equator, as well as 60 degrees north and south, you get air that rises and cools and loses its moisture as it does so. And as relative humidity increases, as the temperature drops, the air will have no choice but to condense and fall out as rain. This happens before the air starts moving horizontally from latitude to latitude, and it drops all of its water, or almost all of it. So when, in the case of the Hadley cell between 30 degrees and the equator, the air that falls at 30 degrees north or 30 degrees south will be very dry. And so the high pressure latitudes tend to be dry, and the low pressure latitudes tend to be wet. Guess which one Antarctica is? Antarctica is a zone of high pressure by and large, especially at the pole. In Antarctica, you have cold, dry air falling at the geographic South Pole, and although the air is indeed transferring some energy from the equator there, long term, the air is still, from our perspective, and absolutely speaking, very cold, and whatever moisture it carried was largely lost at 60 degrees south when it rose high up in the atmosphere for that water to condense. So for the most part, by the time air falls at the South Pole, whatever moisture was in it was dropped at 60 degrees south, which is approximately in the Indian Ocean, the Southern Pacific Ocean, New Zealand, the southern tip of South America. So actually, barely even the southern tip of South America. Actually, the thing is, a lot of the rainfall in the southern hemisphere just ends up on the ocean, and Antarctica itself is quite dry. Some moisture does still travel in the air mass and reach the South Pole, but very little, and the overall rate of snow accumulation is really, really low. And in the areas where that accumulated snow has been blown away, you see that Antarctica is a desert. It's really actually a forgotten desert in the sense that we don't often think of the poles as deserts in the sense that we think of the North American desert or the Sahara or the Australian outback as deserts, but it gets the low levels of precipitation that you would indeed expect in a desert. Antarctica is part of a desert belt that forms around 90 degrees, aka the South Pole, in the southern hemisphere, and in truth, you get a similar desert occurring in the areas that are close to the North Pole, 90 degrees north. In Greenland and the northern extremes of Canada and Siberia, you don't actually get all that much snow there either. And the air is extremely dry and tends to chap your skin in the same way that it does in Antarctica. You'll notice that another set of desert belts occurs at about 30 degrees north in the northern hemisphere and 30 degrees south in the southern hemisphere. And you'll notice that you have areas like the Sahara about at the same latitude as the various North American deserts, like the Great Basin, the Sonoran, and the Mojave. And then the Gobi Desert is about at the same latitude as that. And likewise, you have a similar desert belt existing in the southern hemisphere, where you have the outback or the Great Victorian Desert around the same latitude as the Kalahari Desert and the Patagonian and Atacama deserts in Chile, the latter of which is the driest place on Earth, as I briefly mentioned in Lecture 2. And you'll notice it's not a perfect belt, and that in some areas like Northern Africa, you get a much more consistent desert than in others, because factors like geography play a role also in limiting what water is present. But it's still, in terms of approximations with latitude, they're all approximately the same latitude. There is a belt of dry areas, and that's in part because that is where the air ends up in the Hadley cell, the cell closest to the equator. The air rises at the equator and drops its moisture there, and then the air travels through the atmosphere from the equator to either 30 degrees north or 30 degrees south, and then falls. And by the time it falls, it has long ago lost most of its moisture. It is cold. It is relatively cold, dry air. And of course, the air then might get heated up by infrared radiation because, especially in the desert belts, you still get a lot of heat coming from the sun. But that's kind of a separate fact as to why it's dry. And in the next lecture, we will continue talking about how all this applies to Antarctica and get a little bit more into how oceanic circulation is involved. If any of this seems confusing, I will be doing a lot of review and going over this very heavily during a review session on Monday, April 12th, which will also function as a bit of a quiz preparation review session. So until then, or until Wednesday's lecture, that is. Pardon me. Is the thing still being picked up? Yes, it is.